Will be Eleonore Mangel, who will tell us about classical notions of computation and the Hasegawa-Thiele theorem.
Hello, so this is a joint work with Paul-André Méliès and Guillaume Munch-Macagnonet. So one thing that is almost always assumed in logic is the associativity of coordination, which means that when you have three derivations and you want to compose them, so there are two ways to compose them, either the second and the third one, and then the first one, or the first one and the second one, and finally the third one. So associativity means that the two ways are equal, that it gives us the same thing. So, however, Girard observed that it makes sense to relax associativity in his polarized classical logic called LC. So this fact is, in fact, way more general than that, than classical logic even, and it's deeply connected to effects in the call-by-value and call-by-name scenarios. So when you have a simple program, just let x equal u in T, there are essentially two different ways to compose them. Either to evaluate, either by call-by-value, which means you evaluate u and then T, or by call-by-name, you evaluate T before u. So without effects, it doesn't change anything for the results, if it's well-typed at least. But with effects, the output depends on the order of evaluation, so it matters a lot. So what would happen if we would consider a language with two different lets, one let in call-by-value and one let in call-by-name? So it's not so much a wild idea, and it's already present in many programming languages. So, for example, in ML, it's call-by-value by default, but you can have call-by-name by using syncing. And in Haskell, which is call-by-name by default, you can have call-by-value with the operator $bang. So it's not so much a wild idea, but then when you consider the composition of three programs, three really simple programs, they just print their name, f print f, etc. And you look at the two different ways to compose them, when the composition of f and j is in call-by-value, and the composition of j and h are in call-by-name. Then it gives us two different outputs. On the left, it gives us f, h, and j, whereas on the right, it gives h, f, and j. So the output depends on the bracketing. So it's not an associativity again. So if we want to look at it in a categorical way, so it's well known that call-by-value corresponds to the class-Lie category of a monad, and call-by-name corresponds to the co-class-Lie of a comonad. So if we want to look at both of them at the same time, we'll need to start from an adjunction. So there's a really simple construction with an adjunction that you can do. It's a collage, so it means gluing in French. And so you take the object of A, the object of B, and the arrow between them, and you just add from A to B the arrow A, R, B in A. And then you obtain a category. So we would like to do something quite like that, but for the class-Lie category and the co-class-Lie category. So it's called the duploid construction. So now, on the left, we have a morphism between object of A, which are the class-Lie morphism, and on the right, morphism between B, object of B's, are the co-class-Lie morphism. And the morphism between them are just like the collage. And so on this construction, we have two different compositions, the positive, or class-Lie composition, and the negative, the co-class-Lie composition. And in 3 out of the 4 cases, when we want to compose things, it works, it's associative. But the fourth case, the case where you have negative composition on the left and positive composition on the right, then the two cases are not equal in general. So again, a non-associativity. So we have a second calculus that we call the L calculus, which is a polarized effect calculus to have this phenomenon. So we have an environment on the left, an environment on the right of variables and covariables. And an expression is simply, for an expression, the type of the output, one type of the output is distinguished. For context, one type of the inputs are distinguished. And for the commands, none at all. So we can transform a command in a context by distinguishing one type on the inputs, or we can have an expression by distinguishing one type on the output. And if we have one context and one term where the same type is distinguished, then we can put one in the other and obtain a command. And so it's a polarized calculus, so every type has a polarity. Each type is either positive or negative. So it matters when we have what seems at first like a critical pair. So we have on the left a term mu alpha c, and the right mu tilde alpha a c prime. So if it's on a type which is positive, then we will do a elimination, a cut elimination on call by value, based on call by value. So first, we simplify the expression. And if it's negative, then we reason by call by name, and we simplify first the context. And so when we consider the composition of three commands, so C prime, and C second, then depending on the bracketing, it's not necessarily the same thing. And so again, we have non-associativity. Because as you can see, in the result, the normal form, the order in which the program appears are not the same, which is basically the order of evaluation. And so we would like to have a categorical model for this phenomenon. So we start with a simple definition, just a non-associative category, which is the same thing as a category, but where we remove the assumption about associativity. So we may have path of length 3 that doesn't associate, such that the two ways to compose them are not equal. And so, so now we can consider the reverse, associative path. So a path of length 3, so which does associate, so that the two triangulation of the composition are equal. So it allows us to consider basic properties about non-associative categories. So we say that a morphism is truncable if every path of length 3 that starts with it associates. Usually, a morphism is linear if every path of length 3 that ends with it associates. And for object, we have that B is negative if every path where it's in the second position associates, and usually C is positive if every path where it's in the third position associates. So now we can define what a diploid is. So a diploid is a non-associative category such that every object has a polarity. Every object is either positive or negative, and where we have a positive shift and a negative shift. So shift allows us to transfer object and morphism from one polarity to the other. So the positive shift, it should be, it corresponds to refining something into a value, and the negative shift corresponds to stunking. So as we saw with the diploid construction earlier, every adjunction induces a diploid. And conversely now, every diploid induces an adjunction. So from a diploid, we can construct an adjunction between the category PT of positive object and truncable morphism, and the category NL of negative object and linear morphism. And so the back and forth correspondences between the diploid construction and this adjunction induce a completion on adjunction. So it gives us this result. So we have indirect models of effects in adjunction, direct models in diploids, with a back and forth between them. And if we consider a diploid, and we say that everything is associative, it's called depolarization, then we get categories. And we also have an associated second calculus, so the bare calculus. So it's just the calculus I showed with a few more rules for variables and things, but not much. So that was the work of Guillaume Munch. And so now my work was to add structure on this, to add a tensor, par, arrows, etc. So I have symmetric monoidal closed diploids. So it's considered are in correspondence with linear called by value models. And when depolarized, it simply give us a monoidal closed category, symmetric monoidal closed categories. And we have an associated second calculus in the linear called by value L calculus. And so now if we consider polarized MLL, so we have dialogue diploids, which are in correspondence with dialogue categories, which are continuation model. And when they're polarized, then we get star-autonomous categories. And so the associated second calculus is the linear classical L calculus. And so these ones are a bit complex, too complex to, so I can't enter into more details, but I'd just like to consider with just the tensor, so symmetric monoidal diploids. So when we have a monoidal structure on an adjunction, then it's a well-known fact that the Kleist category inherits a premonoidal structure. So the bifunctoriality of the tensor is lost. And the diagram here does not always commute. So which means that if we have J on the right and then F on the left, it's not the same thing as having first F on the left and then J on the right. And we say that F is central if it makes the diagram commutes for any J. And so now, if we want to generalize it on the whole diploid, then it's not the bifunctoriality, it's the functoriality of the tensor that is lost, which means that the tensor does not preserve the composition. So having F tensor B and then J tensor B is not the same thing as having F composed with J and then tensoring with B. So in models of linear logic and even logic in general, operators are often defined with an adjunction. So, for example, the arrow is defined as the right adjoint of the tensor. But how can it be done when our operators are not even functorial? So that was a big surprise during my research, is that actually we can have adjunction of graph morphism between non-associative categories. And adjunction can be defined without functoriality of the morphism, and they still have very nice properties. So I can't go into more details now, but it's a really nice thing, I think. And so now I want to give an example of the effect of probability. So when we consider the monad of finite distributions. So we get a symmetrical monoidal diploids of sets equipped with the polarity and stochastic map between them. And in this diploid, every map is central. Because whether if you have two dice, whether you roll the first one and then the second one, or the opposite, if it's in parallel, it doesn't change anything. However, the only thunkable positive morphism are the direct distribution, are the constant morphism. So the non-associativity appears even if the effect is commutative. So is there a relation between thunkable morphism and central morphism still? So we have that actually in the symmetrical monoidal diploids, thunkable morphism are central, always. But as we just saw, not all central morphisms are thunkable. But there is a specific case where thunkability and centrality are the same thing. So in the presence of continuations, thunkable morphisms are exactly the central morphisms. So consider morphism F central, and we have J and H after. And so we can use the duality to reverse H and J. And so now we have a J with two inputs, B and C star. And it's just like a centrality problem. We have an input on the right with H star, and an input on the left with F. And so since F is central, we can commute them. We can say that it's equal to that. And then we can simply reapply the duality negation and obtain back the other bracketing of the expression. So this we call the Hasegawa-Tsueko theorem, because they both found this theorem in different contexts each. And it's an important result, and I think it's really great to see, very nice to see how simple it is to prove in diploids. So another way to say a corollary is to say that if every morphism of dialog diploids is central, then every morphism is thunkable, and so the diploid is a category, and it's a star-autonomous category. Or again, another formulation is to say that the continuation monad of a dialog category is idempotent if and only if it's commutative. So to conclude, in the paper, we have 4 main contributions. So we have the syntax and the semantics of the linear classical logic, L calculus, the linear classical L calculus, symmetric monadal diploids with both an arrow and a duality, separately, a theory of injunction between non-associative categories, and 2 proofs of the Hasegawa-Tsueko theorem, one syntactically and one semantically. And in the future, we'd like to add every other operator of linear logic, so mostly sum and exponential. And we also like to integrate delimited continuation to hopefully obtain dependent diploids. Thank you for your attention.
Questions? Maybe I can start with one. So you say that you had a very nice notion of adjunction between graphs.
Yeah.
And like adjunctions are a kind of representability, notion of representability, which usually boils down to some notion of Yoneda.
Yeah.
And for me, Yoneda is very tied down to associativity. Like it works because things are associative, so you can just boil down everything to identity. Can you say a word on what makes it nice and what makes it click in some sense?
First, for the part of the Yoneda lemma, we are currently working on that to find a version of it, and it would be more restrictive than the associative version, obviously. But I think we will be able to have a nice Yoneda lemma in non-associative categories. And then why it's nice? So one thing is that the right adjoint preserve syncability, and the left adjoint preserve linearity. So I think that's really nice. And there are other more complex properties.
Hi, thank you for a great talk.
Thank you.
I was hoping you could say a bit more about what the Hasegawa-Tsueko theorem is and why it arises naturally out of your work, or why could you expand on like?
Yeah. So first, Tsueko was the first one to find this theorem, but it was in the case of without linearity, and he proved it. And then Hasegawa, so it was for the case of linearity, but there was no written proof of it. So this is the first written proof of the linear case. And so I think it's really nice to see the correspondence in continuation between the property of associativity and the property of parallelism, kind of the tensor.
questions?
This is really interesting work. Thanks very much for presenting it. I'm curious about your notion of adjunctions between non-commutative or non-associative, categories. So there's been a lot of work on the two categorical structure of things like adjunctions and monads and comonads, Kleisli and Coase-Kleisli. I'm wondering if you've investigated any of that here, the two categorical structure.
Not really yet, but it's still a work in progress. And so now, in this paper, we only had one level for the moment. But it's an interesting question, and thank you.
Nice talk. One thing I'll just say real quick, I have kind of a question, but responding to that last question is I think that with there's some sort of bi-category thing you can do where you have two linearly distributing structures, but you don't require associativity, and you can still have essentially, and you might not even require unitality, and you can still have pretty much a full theory of adjunctions and monads. But what I was going to ask is, since I'm also kind of interested in this non-associative stuff, is do you have some sort of like trove of example categories? Because I'm always worried that there seem to be a lot of little properties that you could assume that will end up forcing associativity. Like, for instance, if your category has a property where if you take a Hom functor from where you put in as your first object, like the monoidal unit for one of these things, if that Hom functor is full and faithful, even in some enriched sense, this will end up forcing some associativity in certain cases. So, and that seems to happen a lot with examples that I've looked at. So I'm just wondering, where can I find examples, or do you have examples, models, things like that?
So, an example of non-associative categories?
Sorry, for which?
So what's the question exactly?
Do you have a trove of examples of non-associative structures just to sort of verify that it isn't just that we're not assuming associativity, but you actually have a model demonstrating that you can actually come up with it?
Yes, so the diploid construction, so it gives us diploid, and it's associative if and only if the original monad is idempotent. So every monad which is not idempotent generates a non-associative diploid, a really non-associative diploid.
Okay, and so I guess I'll need to try to understand directly what that means, but you have some examples of such non-idempotent.
Yeah, by taking effect, the probability one, the printing one, any effects really gives us non-associative, really non-associative, probably non-associative diploid.
Okay, cool, super interesting. I'll need to check out your paper. Thank you.
We still have time for a short question if there is one. If there is no, let's thank Eleonore again.
Here.
A bit low.
Lower on this.
On this is a bit unstable, so probably
But
on your
how
t-shirt,
can
but yeah, somewhere like
Like this.
yeah, probably.
Is it fine?
Is it?
Take off this.
Oh, because it might. Okay, sure.
Okay. But is it working? Is this working?
It will.
Yes.
1 second. So the second speaker of this session is Nusha Naimei, who will tell us about a type theory for comprehension categories.
Yes. So hello. Yes, I'm Nusha. PhD student at École Polytechnique, and this is joint work with Benedict Arends from TU Delft, Paige North from Utrecht University, and Niels van der Weijden from Radboud University. First, I'm going to talk about the setting we're in. So I guess we can all agree that dependent type theory serves as a foundation for proof assistance and programming languages. And we know that there are many well-established categorical semantics of it, contextual categories, categories with families, display map categories, natural models, and etc. But there is comprehension categories, which are more general than the other ones. And they're what we were going to focus on in this talk. And to motivate this, here we have a quote from Arends Lamsdene. Can you see the cursor? Arends Lamsdene North, which says that almost all established notions of models can be seen as sub-two categories of the two category of comprehension categories. Yes, we will see more about this later a bit also. So let's look at what happens when you interpret Martin-Löf type theory in comprehension categories. So one of the main things I want to focus on is that this semantics arrow then does not use all the features of comprehension categories. So you would have two options: either restrict your models, only focus on a class of comprehension categories and interpret Martin-Löf type theories in those, which is what usually is done, or you can try to make your type theory more expressive and see what useful stuff you would get. This is the second thing is what we do. We get to type theory by this, and we call it CCTT, which CC is for comprehension categories. Okay, so why not just restrict the models? There are two natural questions that would arise at this point. Are there interesting examples that we would miss if we do this? Or are there interesting features that you will lose in our type theory if we do this? So I will now tell you first some preliminaries what a comprehension category is, and then we will come back to these two questions. Okay, so what is a comprehension category? It consists of a category C that you see here, a cloven fibration P that you see here, a functor chi from T to C arrow here, which makes this diagram commute. And also chi has to preserve Cartesian arrows, which I will not focus on because for the purpose of this talk it's not important for us, but this also is something that is in the definition. But something which is important for us, and I would like to point out, is when we call a comprehension category full, we say comprehension category is full if this functor chi is fully faithful, and we see that it is split if the fibration P is split. And comprehension categories which are both full and split are models for Martin-Löf type theory. So let's gain some intuition about what all this stuff that I was just saying actually is. So you can think about this category C as a category of context and context morphisms. And whenever you have a context gamma in this category, you can think about the fiber over it here as a category of types in that context. Then the reindexing functors of your fibration give you substitution. And if you have an object A, like a type A here in context gamma, this chi guy here will map it to the projection from the extended context gamma.A back to the original context gamma. What about the terms of the type theory? So the terms are interpreted as sections of such projections. The terms of type A are sections of such a projection here. And this will become important in a moment. So what about vertical morphisms? These morphisms within the fibers. So if you have a fiber like this over an object gamma in C, what about these morphisms here? I did not mention them in the previous slide. So these are exactly the features of a comprehension category that at the beginning I said this semantic arrow does not touch. Yes. Yeah, so these are important in the rest of this talk. But before that, back to our motivations. I mentioned it a bit before, but what I precisely mean is that a comprehension category can express both morphisms between contexts, so the morphisms here, and morphisms between types, so the morphisms here. But whenever you restrict to full comprehension categories, you are essentially killing off one of these extra dimensions of morphisms that you have. Why? Because then these morphisms between types are actually like uniquely determined. They can be recovered from the terms of the theory that you have, like from these sections of the projections I showed you before in C. And we argue, and we will argue with C, that that if you not kill off this extra dimension, if you keep them, then these could capture coercive subtyping for you. And back to our first question, are there interesting examples with this extra dimension of morphisms that we have? Yes, there are interesting examples. Intentional type theories, such as homotopy type theory and cubical type theory, are often interpreted in some categorical structure which are called algebraic weak factorization systems. I will not talk about them in this talk, but I will tell you that whenever you have an algebraic weak factorization system, you can get a comprehension category. And you may know that, okay, whenever you have a CWF, you can also get a comprehension category, but with these ones, the ones that arise from algebraic weak factorization systems, unlike the ones that are coming from CWFs, you would actually get a non-full comprehension category. And I can even show you what it looks like. For your category of types here, you would get the Eilenberg-Moore category of this monad R, and for your comprehension that you'll get here would be a forgetful functor. So you see that it's not a full comprehension category. And these are interesting examples that are in the literature and well studied. Yes. So I already told you an interesting feature you will lose is coercive subtyping, but what else? Maybe we have other things. So we also argue that having both terms and type morphisms could buy us a tighter control over definitional equalities. What do I mean by this? In homotopy theoretic models of Martin-Löf type theory that come from algebraic weak factorization systems, these type morphisms, these vertical morphisms that I was showing you before, they have this special, they are like special in a way, that they preserve transport of structure along the term of identity up to definitional equality. So usually this would be only up to propositional equality, but for these type morphisms are ones who preserve this up to definitional equality. And what does this mean? What does this mean? It means that you could just add such a rule to CTTT. You could add a rule that says these type morphisms commute strictly up to definitional equality with transport, and that nothing will break, everything will still be fine. Why? Because this rule is actually validated in these models that I was talking about. And an example of this commonly used function in MLTT that it's used a lot, and you would really want it to commute up to definitional equality with transport is the first projection of sigma types, and this is indeed for us a type morphism. So we could add this rule, and things will be fine. Okay. So now I'm done with the motivation stuff. I will now tell you what will. I'll tell you what will happen in the rest of this talk. I will tell you about CCTT, which reflects the structure of comprehension categories, and then I will tell you a bit about how it captures coercive subtyping. Here we are extending the work of Coralli and Emenegger. I'll also tell you about that. And then we talk a bit about type formers. So we extend CCTT in the paper with pi, sigma, and identity types. Here I will just show you sigma. Okay. So what does CCTT look like? These are our judgments. The first four should be familiar. You have seen them. It's just also, they are there also in Martin-Löf type theory. These two are not familiar. And this fifth judgment is actually corresponds to these vertical morphisms I was showing you before. So such a judgment like this is interpreted as this morphism T up here from A to B in a fiber over gamma. So we get a judgment for these vertical morphisms. And to just give you like a bit of a feel of what the structural rules look like, I'm gonna show the structural rules that correspond to the category of context. But then we have similar ones for category of types and other things. So the first two rules, the first line, it corresponds to the identity and composition in the category C, and the other ones are the unital and the associativity laws in the category C. We also add, okay, then I'll not show you. You can see the rest of the rules in the paper if you want. We have rules for substitution and context extension and all the things that you might want. But we will now just go through some of them through the lens of subtyping so that I can convince you that we capture coercive subtyping. We also have this soundness theorem that every comprehension category models the rules of CCTT. Okay, so subtyping. It starts with Corelli and Emmenegger, who were studying generalized categories with families, which is a categorical structure equivalent to comprehension categories, the general ones. And they said that these vertical morphisms there can be thought of as witnesses for coercive subtyping. And that means that whenever you see this, you saw this judgment before that we had in CCTT, you should think of it as T being a witness for A being a subtype of B in context gamma. So when we have a subtyping, I should show you a subsumption rule. And we can derive this subsumption rule in CCTT, which says if you have a witness T of type A being a subtype of type B, and also you have a term of type A, then you can get a term of type B like this, which is just the composition that you see below. And it's maybe good to note that whenever you have a witness T, the comprehension of it, so this morphism that you get here in C, is acting like a coercion function for that witness. So we also have substitution for subtyping, which looks like this, and also weakening. These are just what you would expect. So yes, I will not read the rules. It's just what you would expect, but we also have these. Okay. So now I will briefly tell you what we do when we want to extend the structural rules with type formers. So something which was important for us was that we were making a distinction between the normal, like if you just forget about the subtyping stuff and you just want to add sigma types the way you would, and then what you would need to add when you want to have all the subtyping for sigma type stuff. So when we just add the sigma types, for example, sigma types or whatever type former, I'm now gonna use sigma types as an example. Naturally, we don't add rules that involve this judgment for the vertical morphisms that you saw before, and then we're gonna add all the subtyping structure to it. Okay, so this is how we would add sigma types to our rules. So this is just what you would expect it to be, the formation rule, the introduction rule, elimination rule. This is just what you would expect, again, for beta and alpha. And then this one is, this corresponds to a Beck-Chevalier condition. It just tells you that substitution commutes with sigma as you would expect. So we also have these Beck-Chevalier rules for Beck-Chevalier conditions. Yes. Now, what would you do when you want to add the subtyping rules, the rules for subtyping? So let's say you have a witness F for A being a subtype of A prime, and you have a witness G here for B being a subtype of B prime. Then you would expect to have such a subtyping relation between sigma AB and sigma A prime B prime, because sigma acts covariantly on both arguments. So this is exactly the rule we add, but we also expect that the coercion function attached to this witness actually acts in a certain way. So we would want it to first project the pair down, then do the coercion on the second argument, then do the coercion on the first argument, and then pair back up make the pair again. So we also add this rule that the coercion function for this subtyping relation, which was what I showed you before, the comprehension, actually does this. And we also add rules that say sigma is functorial. Yes, so this is how we get the subtyping stuff for sigma types. Okay, so this is on the CCTT side, but also on the semantic side, we have these definitions which are like what it means for a comprehension category to have subtyping for pi types, sigma types, identity types, which, so these definitions also mirror what I was showing you before on the rule side, but now these are on the semantic side. And we also have, again, soundness theorems that are like any comprehension category with subtyping for sigma types models CCTT extended with subtyping for sigma types, also for pi and ID. Yes. Okay. So I will now close with some related work. So there has been a lot of work on subsumptive and cursive subtyping and their semantics. So Salberger and Méliès give a favorable view of subsumptive subtyping as opposed to cursive subtyping that we study. And Corellia and Emenegger, they, as I told you, they were first observing that these type morphisms can be witnesses for cursive subtyping, but in generalized categories with families. Laurent, Lennon, Bertrand, and Maillard, they extend Martin-Löf type theory to a type theory with that has definitionally functorial type formers, and then they use this to extend Martin-Löf type theory to a type theory with cursive, and then another one with subsumptive subtyping. See, I cannot pronounce it. This is why we're doing coercive subtyping. Yes. So there's a close relation between our work and their version of their type theory with the coercive subtyping. Then Adjej, Benjamin, Lennon, Bertrand, and Maillard, they develop a type theory which is modeled by split generalized categories with families which are equivalent to split comprehension categories, and then they also provide a general framework for defining type formers that are automatically functorial. This is also POPL this year, so we are also closely related to them, our work. Yes, I think this is all I wanted to say. We design CCTT, it reflects comprehension categories, structure of comprehension categories, and then we say if we don't kill off this extra dimension, then we get coercive subtyping. Thank you.
Lovely talk. Thanks for the talk.
Yes, I can hear this.
I finally understand comprehension categories a bit better. I was wondering whether you looked at algorithmic aspects of these type theories.
Yes, we did not. But yes.
Okay.
Yes, thank you.
Yes. So yeah, thank you for your talk. So so you described in slide 19 how sums work. Yes.
Yes.
Sigma. Yes. Sigma
Yes.
types. So
You want me
so
to
I
show?
guess you. Yeah, I think it's good. You can come back to it. So do you have something similar for?
Here?
Yes.
Yes.
And so yeah, something for pi types, because pi types are very interesting, and surprisingly they are connected to linear logic. So I was wondering whether you noticed that.
Yes, we have. It's similar, but here it's just, for this page, the difference would be this part. So it's just contravariant, but then the rest is the same. We also have the comprehension category with pi types.
Okay, but there is a subtlety about the way, I mean, yeah, okay. There is,
Yes.
I mean, in fact, what happens is that the type that you get is exactly the type that you would get for implication, but contravariantly in linear logic, like as a negation of the tensor. And I wonder whether you observed that in your work.
Yes. We did not we did not we were not looking for it,
Yes.
but I think you would still observe.
Okay,
Maybe
okay.
we can.
Because I think it's quite a
discuss.
beautiful thing that, you know, at the heart of dependent types, we have something coming from basic ideas of continuations. Yeah.
Yes, we can discuss
Okay, so
later.
you saw that. Okay, good.
Yes. Thank you.
Hi, thank you for the talk. You had soundness results. I was wondering, what are the obstacles for completeness?
Completeness.
Yeah.
Yes. So we discussed a bit how we would go about how we would proceed for a completeness proof. I guess we have just not done it because it was kind of out of scope for us. But we give like a sketch of how you would do it and which it would be similar to like which other related work we have done it.
Okay, thank you.
Yes. Yes. No questions?
Any other question? So I had one. At the beginning, you said that you gave as a motivation this example of algebraic weak factorization system for non-full category, comprehension categories.
Yes. Here. Or
Of
no?
course, I immediately see that it is not full, but do you have a slightly more explicit example that I could like squeeze out and concretely observe?
Yes. So there is one. Okay, I will tell you one now. So imagine you can work it out, and in the end you would end up with this. So this category C here would be the category of groupoids. Okay. Then the C arrow would be like all the groupoid functors of them, and then the morphisms would also be like these commuting squares. But then you see that EMR is then groupoid functors that are equipped with the structure of an isocleaving. So the morphisms here then would be only the ones that strictly, like on the nose, preserve this isocleaving structure. So then this also then forgets all of these for you. Yes, this is one. You can also do it with cubical sets and cubical sets, and then the category of types would be cubical sets equipped with a fibrancy structure.
Okay, thanks.
Yes.
So if we don't have any other question, let's thank the speaker.
Yes, I will give it to you. Thank you.
That's the.
Is that the right one?
No, it's,
No, it's not.
I mean, it is the right one. It's just you're not
Never
plugging it
works.
from the right side.
Okay.
Yeah, because.
Okay, fine.
But yeah,
Yeah.
I think I'll take off the badge because it interferes, and then not the like other way around. This way. Yeah.
Okay.
It's better that it goes towards it should be fine.
Maybe up here? Or?
It's fine. Yeah, just what's this? Way too complicated.
Chose the wrong clothes today, it seems. Okay, good.
So Inigo Bat will be giving the next talk on high-order behavioral conformance via vibration.
Right, thank you. Hello, everyone. So there are lots of technical terms in this slide, but what this talk is really about is a categorical approach on one of the most fundamental questions in programming language theory, namely, I'm giving two programs, are they behaving in the same way? Or if they're not behaving the same, how different are they behaving? And can I quantify this kind of, and in particular, how can I prove how different they behave? So if you're an AI person, maybe how can I explain it? Yeah. So That's the subject of the talk today. And let's look at the special case of equivalence of programs. So what does it mean for two programs to behave in exactly the same way? And, well, one very general and natural notion of equivalence for programs that pretty much applies to every programming language is contextual equivalence, which says two programs are equivalent if they are behaving in the same way in every context. So a context is just a program with a whole. Think of a test if you want. And being equivalent says no matter which context I put P and Q into, if one of them terminates, then the other one terminates. Yeah? So the intuition is that I can find no test that distinguishes their termination behavior. And, well, as I said, this applies to pretty much every higher order language, like, for example, the Lambda calculus, just to give you an example. So this is equivalence, but there are many situations where we are not really interested in exact equivalence, but in how different programs are. So are they somehow a bit different, or are they vastly different? This question in particular makes sense in the context of languages with quantitative features, like probabilistic lambda calculi. So here's an example of a probabilistic lambda calculus. You just extend your standard syntax with a choice operator, where the intuitive semantics is you just flip a coin and then do P or Q with probability 1/2 each. Yeah? So in this calculus, a term will not converge to a single value. It will converge to a distribution of values. Yeah? So you can say I go with probability 0.3 to this value and with probability 0.7 to this value, right? And so in this setting, we can introduce what is known as a contextual pseudometric, which says the distance of P and Q is computed by just taking contexts and computing the difference in termination probability. Yeah? So here the intuition is, if we think of a context as a test, if two programs are very different, then there should be some test that makes, say, P terminate with high probability and Q with low probability, so the difference should be pretty high. Yeah? And so you take the supremum over all contexts, and this gives you the contextual pseudometric. So this is a very simple natural notion, but unfortunately, it is quite hard to compute. Yeah? So let's think of an example. We take the always diverging program, and here the program omega plus identity function. So intuitively, the distance should be 1/2, right? Because this always diverges, and this diverges with probability 1/2. And actually, the lower bound is easy to prove, because even if you put them into the empty context, there's already a difference of 0.5, right? But it might be conceivable that there is some context that produces a bigger difference. So the upper bound, that this is exactly 0.5 and not more, is not easy to prove, because you would have to prove something about all contexts at the same time. So what is needed is some cleverness, and the cleverness is provided by co-inductive techniques that give you efficient proof methods to prove this kind of upper bound. And there's actually a whole bunch of literature on this subject, starting by the work of Abramsky in the 1990s, who thought about the qualitative notion of contextual equivalence. And he introduced this co-inductive technique of applicative bisimulations, which in connection with this House method proves that applicative bisimulations are a sound proof method for contextual equivalence. And down here you see a bunch of dots. This just means that in the last 35 years, people have extended this House method and the method of applicative bisimulation to many, many different kinds of languages with effects and other kinds of features. And more recently, there's this work by Courbeillet and Dalago, who extended House method to applicative pseudometrics, so this quantitative notion of distance of programs, and also proved this to be a sound proof method for proving upper bounds to contextual distances. So this is very nice work. So let me briefly explain how this roughly works in the setting of the probabilistic lambda calculus. So here's our probabilistic lambda calculus. We have seen the syntax, and the operational semantics is very intuitive. So it just explains for every term to which distribution of values it will converge, right? So for example, there's a rule that says if my term P goes to the value lambda x dot P1 with probability 0.3 and lambda x dot P2 with probability 0.7, and say Pi of Q goes to Vi always, then P of Q goes to this distribution, right? And if you read this, you see it's very natural. It's how you would define the operational semantics. So it's nothing surprising here. And then what Grubelier and Dalago did is they introduced this notion of applicative pseudometric, which is a pseudometric on program terms. So lambda is the set of programs that is supposed to have the following property. So if you take two programs, P1 and P2, and compute their distributions of values that they converge to, then you apply each of these values to some input E, any input, and this gives you another two distributions, and then you compute the Kantorovich distance of these two distributions, right? Which is just a standard way of lifting a distance on a set to a distance on the distributions on that set. So this is a very standard way of doing this. And so this kind of non-expansivity property is what they required of an applicative pseudometric. And then the key step is to show that this pseudometric is a congruence, which just says that it's non-expansive with respect to all the operations of the language. So for example, the distance of PQ and P'Q should be at most the distance of the two operands. And the way how they do this is they invented a quantitative version of this House method. And this version, House method in general, is pretty complex. And in this case, for example, the proof uses linear programming duality. So it's really not a trivial argument. In general, my intuition why this House method is often considered complex is it tries to marry a first-order notion, namely a notion of bisimulation or bisimulation metric, to a higher-order language, right? So there must be some complication there, and this is exactly the complication. So and after that, actually proving the soundness is usually easy. So that the pseudometric gives you an upper bound to the contextual pseudometric. This is easy, essentially because the contextual pseudometric is the smallest pseudometric that is a congruence and respects termination probabilities. And D is also one of these, so it must be an upper bound, right? So yeah, so this is the idea of House method in the quantitative setting. So this is a quite powerful, widely applicable proof technique. But standardly, every language needs its own incarnation of House method. So whenever you have a language and you change a bit in the syntax, the behavior, you need to reinvent House method. You have to give new definitions, and you have to redo this often very complex soundness proof. And also, if you change the notion of conformance, so if you go from bisimulation to pseudometrics, or maybe something even more complicated, quantile valued metrics or whatever, you would also have to adapt all this, right? So wouldn't it be nice to have something like this, right? And there has been some work in this direction, starting with this Lix and POPL paper 2 years ago that I did together with a bunch of collaborators. So we introduced a kind of language-independent, syntax-free abstract approach to these co-inductive techniques, which were based on algebras, coalgebras, and relation lifting, so very general categorical concepts. But they were limited to small step semantics and applicative simulations. So they didn't apply to bisimulations. They also didn't apply to pseudometrics. And this is exactly what I'm going to lift today. So today, I'm going to tell you how to do this for big step semantics, like the semantics of the probabilistic lambda calculus. And I'm also going to tell you how to extend this from applicative simulations to general conformances, which include pseudometrics, for example. And the key technique that we use is fibrations. So there's another talk about fibrations today. So of course, in order to do this, we need a categorical understanding of all these terms that are displayed here in blue. So what is syntax and semantics even categorically? What is House method and so on, right? So let's start with the syntax and semantics part. So here on the left, we again have our example of the probabilistic lambda calculus. So we have the terms, we have the rules. And what these rules really do is they generate, they define an operational model, which is just a transition system on terms that says for every term which distribution of values or functions I go into, right? So D is the probability distribution or subdistribution functor because there might be some probability of non-termination. So how do we think about these structures categorically? Let's start with the syntax part. This is luckily something that Fiore et al. have been doing, have done 25 years ago. So they suggested to model syntax of languages with binders as initial algebras of binding polynomial functors on pre-sheaf categories. So in their case, they would take some binding functor on pre-sheaves over injections, and this would give you this syntax as an initial algebra. And so let's be bold, let's be courageous, forget about this pre-sheaf stuff, let's take any endo functor on any category and take its initial algebra and regard this as the abstract object of program terms. Yeah, so the mu sigma here would be the lambda in the example. What about behavior? So how do we abstract from this operational model? Well, we can observe that this expression here, the d of lambda to the lambda, is bifunctorial. Namely, if we take this bifunctor here, d of y to the x, we can write this as lambda to b of lambda lambda. So and this again explains itself how to abstract it. We just take any bifunctor whatsoever, which is contravariant in the first and covariant in the second component, corresponding to the fact that functions can be inputs and outputs of functions in higher order languages, right? And we take any what I call higher order coalgebra, which is just a morphism of this type, which is a higher order version of the usual notion of coalgebra for an endo functor. Okay, so this gives us kind of syntax and the operational model abstractly. But what about the rules? So what do we need to model this kind of rule by what I call an abstract higher order specification? Well, what kind of structure do we need here? First of all, these rules involve terms of some kind, so certainly we would want to need something like, we would need something like a free monad probably. So sigma star is the free monad generated by sigma. Think of program terms, right? More importantly, what we need is to think about unraveled behaviors, because if you look at the premise of this rule, it says you unravel the behavior of P for one step, so you tell me what P, which distribution P goes to, and then you take these PIs and also apply them, right? So you need to unravel two levels of behavior in this case. And in general, one can model this kind of structure by kind of higher order version of a co-free coalgebra, which is like a final coalgebra with parameters if you want. So think of this as the object of unraveled behaviors. And so overall, we can model rules, big step rules like this, by a dinatural transformation of this type that intuitively says, I just encode the rules into a family of maps. So I say, you give me an operation of my language, like the P of Q application. Then you tell me for each of the operands how they unravel. So for example, you unravel the P for two steps, for two layers. And then I give you the output of the rule. So in this case, the distribution that I go to. Yeah? So this is quite a pleasant abstract way of modeling operational semantics. This is kind of 50% of the contribution of this paper. But honestly, when I came up with this, I thought, yeah, this is pretty, but it must be too general to be useful, because the goal is ultimately to develop co-inductive techniques like House method at this level. And amazingly, it works at this level. So not only do we get big step operational semantics abstractly, we also get a theory of applicative conformances at this level of abstraction. And so let me explain how this works. So now, for the rest of this talk, let's assume that we are given such a specification, so an abstract form of operational semantics, and we are given its operational model, so the model that it induces on the program terms. And so how do we do pseudometrics, applicative pseudometrics? We do the following. Let's, for now, assume that our language lives in the category of sets, just for simplicity, not pre-sheaves or anything. we take the category of pseudometric spaces and non-expansive maps, and we lift our behavior functor in some way to the category of pseudometrics. So, for example, if we take the behavior functor of the probabilistic lambda calculus, which was d of something, we take what is known as the Kantorovich lifting, which is just a way of computing this Kantorovich metric. Do we have it? Right. So we said we lift every metric to the Kantorovich metric on distributions, right? And this is exactly what this Kantorovich lifting does abstractly. So there is actually a categorical way of constructing these liftings from predicates, but in this setting, I don't assume any concrete construction, so it can be any lifting whatsoever. Yeah? Good. And so this is the data that we use to model pseudometrics. We take a lifting to pseudometrics, and now we can define an applicative pseudometric in this generality to be a pseudometric on the space of programs, such that the operational model, this higher order coalgebra, is non-expansive as a map from the space of programs to the space of behaviors, right? And if you go back to the probabilistic lambda calculus, this is exactly what this property here says. The non-expansivity means exactly this, right? So, but we can say this at the level of abstract higher order coalgebras. I should mention that this idea of using liftings to model applicative pseudometrics or pseudometrics in general, behavioral pseudometrics, goes back to this older work by Baldan et al. From 2014, where they did this for first order coalgebras, so standard label transition systems, but it applies very smoothly to this higher order case as well. Right, okay, so this gives us already an abstract way of talking about applicative pseudometrics, but actually, if you look at this, we didn't really use anything about the fact that this is the category of pseudometrics. We can replace it by pretty much any nice enough vibration. So we can replace pseudometrics and sets by any vibration over any category C. There will be some assumptions that I will come to later. So if you don't know what a vibration is, the general idea is it's a category that allows you to lift or pull back structure from the base category to the total category. Yeah? And this includes examples like all kinds of metric spaces with or without some axioms, all kinds of arbitrarily complicated relational structures like fuzzy relations, quantile valued relations, or structures with many relations at the same time. This is all covered by this vibrational framework. So it's a very general notion that allows you to cover many different forms of conformances like bisimulations, distances at the same time. So how does this work at this level of generality? So we have the notion of applicative conformance, parametric in the vibration, and again the lifting. And an applicative conformance is just an object in the vibration above my object of program terms, which lives down here, with the property that the operational model lifts to the vibration, so lifts from C to E. Yeah? So there is some gamma bar above this model on the object E. So for example, in the pseudometric case, this is exactly this fact that it's non-expansive, right? Okay. So again, this means that we have a nice abstract way of talking about applicative pseudometrics, bisimulations, and so on. And now, the key observation is that the congruence result, which was the key to the soundness for bisimulations and similar notions, works at this generality. So it says, roughly, if we have a nice enough vibration and a nice enough language given by this higher order specification, then the greatest applicative conformance, which is the generalization of the greatest pseudometric or the greatest bisimulation, is a congruence in the vibrational sense. Yeah? So this is the main theoretical result of this work. Let me very briefly explain how this is proved. So, well, let me first briefly explain what nice means. So nice means that, first of all, the operational rules should respect the structure given by the vibration. So, for example, in the probabilistic case, it just means that the rules are non-expansive. So if I change the premises a bit according to the Kantorovich metric, then the conclusion should also only change a bit. Also, a nice vibration means that the fibers must carry a monoid structure that corresponds to composing relations of pseudometrics. So you need some structure like this that allows you to imitate House method, because this is exactly what the proof does. It's a vibrational imitation of House method. So House method basically says, I take my bisimulation relation, I form its House closure, which is an operation that involves composition, for example, and then I prove that the House closure does it. And this turns out to be working amazingly nice at this vibrational level. And so in total, what we get is kind of a common roof over all these notions of applicative pseudometrics, plus the House method. It's highly parametric, and because it's highly parametric, it applies to all kinds of languages. I walked you through this probabilistic example in this talk, but it also applies to other kinds of effects like non-deterministic, stateful. It also applies to different kinds of evaluation. So it's really a nice uniform framework to this kind of co-inductive reasoning. And what you get overall is like a method to proving upper bounds to contextual conformances. Yeah? Right, so I'm almost done. Let me just give you the big picture. So this talk is part of a research program that me and my co-authors started like 3 years ago at POPL', which we call Higher Order Mathematical Operational Semantics, which is about, say, developing operational semantics and the theory of operational reasoning at as abstractly as we can. So today I showed you how this works for House method and probabilistic behavioral metrics. One thing that I also want to do and basically know how to do is logical relations, which we envision can be applied to parametricity results abstractly, because parametricity is ultimately an exercise in logical relations of a very complex form. Right, and there are other directions to go, which I will not read out. Okay, thank you.
So you mentioned the work by Krubi and Del Lago, yeah?
Yeah.
And so, I mean, it's just to be clear, like that your approach subsumes it, or can you reprove what? I mean, just,
we cover the results.
So, okay, because it was not, I mean, I understood that, but, so my question is, you mentioned linear programming and forms of duality in their proof, and I wonder whether you have that kind of dualities in your work
yes.
too.
So that's a good question. So in their proof, it appears a bit ad hoc, and in my proof, it appears in checking this condition, this niceness condition on the vibration. And ultimately, it appears in the form where you just use Kantorowicz-Wasserstein duality between the two dual presentations of the metric. This is where it's used. Yeah.
Okay.
But it's used in a much more principled way.
Yes.
Yeah.
Okay.
Thanks for the talk. You had at the beginning like positives and negatives of Howe's method.
Yeah.
One thing that you didn't say that many people, some people, one might say is that Howe's method normally seems kind of magical. I mean, you pull it out of thin air and it works. After all this work, does it still seem magical or does it seem more natural?
Well, I mean, yes and no. So I think the fact that it works at this with this little structure makes it a bit less magical. But I have to admit, still, when I see it in use, I have usually very little intuition why this actually works. So when you compare it to like logical relations, which is the other de facto method to prove contextual equivalence, it is less intuitive. But I would argue that, I mean, you often get this result now for free, right? And I would argue that when it comes to actually using bisimulations, this is easier than logical relations. That's at least my view of things. So once you have this House method proved, it's easy to use bisimulations. Yeah.
Thanks.
Thank you for the talk. At the beginning, you said that we move from contextual equivalence to applicative bisimulations to have easier proofs. And that's true for some programs, but not for all of them. Sometimes applicative bisimilarity is as hard as proving contextual equivalence. And so there is normal form-based simulation. There are normal form-based simulations that provide some easier proofs, say, for fixed point operators. And I'm kind of wondering if the whole higher order abstract syntax, is it like biased towards applicative bisimulations, or do you think there would be a way to switch it for normal form-based simulations?
Yeah, that's a very good question. So it probably is even one of these bubbles. Okay, not normal form, environmental bisimulations is also a way of simplifying this method. So we haven't gone in this direction so far, so I cannot really answer whether it's biased, but we try to extend our methods to more complex, like environmental or normal form bisimulations, to simplify this method further. But right now, I cannot answer whether this works.
Let's thank the speaker.
Okay, thank you. All right.
Is that good? Works well? Yeah? Okay.
Right. Should be fine.
You think that's a problem? Is that okay? No, sure. Thanks. Okay.
Have a...
Yeah, start. Yeah. Okay, hello everyone. This is joint work with Morgan Rogers from Sorbonne Paris Nord. And the question might seem a bit surprising if you already think you know what a monoid is. We'll come back to that. So basically, I'm going to start off like this. So I'm going to have, first of all, a programming languages introduction, and then a mathematical introduction, right? So, and in between, I'll just talk about categories and multi-categories. And then we'll get to the main story, which is 2 stages of generalization beyond what were the multi-category level, which was sort of well-known previously. Then, if we still have time, I'll just have even more layers of abstraction just for fun, and then we can finish, okay? Right, so let's start with something simple. So if we just have a language of commands, and so we use, let's say, semicolon for sequencing. So m semicolon n simply means do m followed by n. And we have a command that does nothing, skip, right? So then there's kind of 3 obvious equations that you would write down. You would say, well, sequencing is clearly going to be associative, and it has the left identity rule and the right identity rule. So you look at that, and you see clearly monoid structure, right? It is straightforward. You look at a simple sequencing, and you see monoid structure. But sometimes sequencing is more complicated than that. So in call by push value, let's look at the sequencing. So I'm not going to give a whole talk on call by push value, sorry. But the only thing that I want to sort of say or remind you is that a computation of type FA is aiming to return a value. So F is the type of FA is the type of returners. Okay? And this talk is not about the whole of call by push value. Just this little part, right? Just F. If you like, you can call it the core. I don't know whether it's the core, but let's call it the core for the purpose of this talk. So here we have sequencing, right? M has type FA, and N is waiting for a value of type A, and then we run them together. So M runs, it gives a value out, and N then runs, and N could have any type, computation of any type. And you have return. If V is a value, then return V as a computation. And there are 3 equations that relate sequencing and returning. And when I wrote it down years ago, I gave these the obvious names. I called this one associativity, like you would, wouldn't you? I mean, what else would you call it? And I called this left identity, and I called it right identity because it seemed like the obvious name. But is this actually are these names really appropriate here? Like, what has this actually got to do with a monoid? Is it just like a vague resemblance, or is there something genuine going on here? Can we really say this is monoid structure? I want, the last thing to sort of raise the kind of suspense level, I want to focus on the associativity law, right? The associativity law puts together three terms, computations, M, N, and P, right? Now, the left one is a bit different from the other two because N has this sequencing variable X, right? P has this sequencing variable Y, but M, the one on the left, has no sequencing variable. So we see here in the associativity law, the left term is special, no sequencing variable. Also, the right term is special, like M has F-type, N has F-type, but P can have any type. So the right term is also special. So this is what, we didn't see this in the simple language of programs, right? This is very specific to Colbert-Bush value. We're seeing that when we have the associativity law, the left term is special in one way, and the right term is special in a different way. So this helps us to think, this is really getting us to think about this question. If we are going to be able to say that this is a monoid in some way, whatever that means, we somehow need to account for these two aspects, the left being special in one way and the right being special in another way. Okay, that's the programming languages introduction, right? Now it's category theory all the way. Right. Okay, well, before we get that, right, I'm going to give you a definition of category, right? Just to emphasize 2 points. So I'm just basically going through the definition of category and multi-category. I just want to take 2 points. So first of all, size issues are a big deal in this story. And when we deal with category theory, we always have to worry about size issues, and it's a pain. Secondly, in a category, a morphism goes from one object to one object, right? So let's quickly remember. So a category, if I want to emphasize these restrictions, I'll say a like category, right? That's got a class of objects and sets of morphism. I call these Hom sets. They don't have to be disjoint. They're just sets of morphisms. And then you have identities and compositions, and you have the 3 laws. So with this definition, we see that set is a category. And then, sometimes in the narrative, this is where it becomes a pain, you want to talk about things where you have more than a class of objects or more than a set of morphisms, and then you start talking about arbitrary collections, and you say this is a hyperlarge category. So, for example, you've got the hyperlarge category of all categories, right? So if I just say category, I will mean this kind, but if I want to be more general, I would say hyperlarge category. Okay. Multi-categories, the basic difference is that in a multi-category, morphism goes from a list of objects to an object. Not from one to one, but from a list to one. Sometimes we write it like this, from left to right. And in this paper, we mostly have diagrams going downwards. I mean, every author has a different convention where they go leftwards or downwards or whatever, but we're going downwards. So we've got a class of objects, Hom sets for every sequence and object, and then identities are unary maps, and we compose at a single port, right? You've got a morphism G going from a list, and there's one of the inputs, and we compose into it. That's how composition works in a multi-category. And then we've got a bunch of equations, and I'm just going to list them. So you've got, call it left and right identity. I mean, left and right doesn't really work here. It should be upper and lower because we're going downwards. Sorry about that. But I'm so used to saying left and right identity. We have associativity like that, sort of one into another into another. And then finally, we've got this kind of interchange law where you have 2 different things, and it doesn't matter which way around you do the composition, right? So that's what a multi-category is. Many of you will already be familiar with that. Some of you won't be. I should say, just again, if you're not familiar with monoidal categories, you can ignore this slide, but a lot of you will be familiar, so I need to say. So sometimes in a multi-category, you can tensor together objects. I'm not going to go into the details. And Hermida called that a representable multi-category, and he showed that such a multi-category corresponds to a monoidal category. Now, various things are possible. So you have examples of multi-categories where the tensors exist and they're straightforward, examples where they exist and they're complicated, examples where they don't exist for size reasons. That's very common in the examples that in this talk, and also examples where they don't exist for other reasons. All of those things are possible. Because of these two here, not so much because of this one, which isn't really relevant, the last one is not really relevant to this talk, but because of these two, it's more convenient to work with multi-categories rather than the more restrictive monoidal categories. Okay, so now we can start off, the introduction properly. Right, so what is a monoid? The simple answer that you're all waiting for, right? A monoid is a set, called the carrier, equipped with an associative binary operation, which we call the multiplication, and a unit. And then a homomorphism between monoids, that's a function that preserves structure. The thing is that in all kinds of situations, we encounter something that seems to, it's not a monoid, but it looks like a monoid, right? We have a carrier, we have something that looks like a multiplication and a unit, and we have three equations, and we naturally call one of those equations associativity, and the other two, we call them left identity and right identity. So we see the pattern of a monoid, even if it's not actually this. And here are some of the examples. I could expand this list, but we have rings, we have quantiles. Oh, that's a typo. That should say monad on a category A. And category on a class of, you fix a class of objects and you consider category on that class of objects. So we have this notion of a monoid and a multi-category. Actually, Damian yesterday gave a version of this in a monoidal category. We're doing it here in a multi-category. So I saw this in Layster 2002. I'm sure it's much older than that, but this was the earliest thing I could find. So in a multi-category, you can talk about, it's an object with a binary operation and a nullary operation, satisfying the three laws. So multi-category gives you enough structure to define monoid. And again, you can define homomorphism in the same way. You cannot, by the way, describe distributive law in a multi-category. There you really do need something different, such as a monoidal category. But we're not dealing with distributive laws, just monoids. Okay, so then we get these examples, like monoid is a monoid in sets. Ring is a monoid in abelian groups. This is quite common when you learn about monoidal categories or multi-categories. You see this list of examples. Quantile is a monoid in complete sublattices. A monad on A is a monoid in endofunctors. A category on the class E is a monoid in the multi-category of set-valued endomatrices on E. This one is not representable, so we really do need, it's because E is a class and we have Hom sets. Because of that, this isn't a monoidal category, but it is a multi-category. So this one illustrates the point that we do want that generality of multi-categories. So many of you will have heard this saying, a monad is just a monoid in the category of endofunctors. What's the problem, right? It just shows how well known this idea is. Okay, that's all background. That's all the past. But sadly, when you work with multi-categories, that doesn't include all the examples of interest. So here are 5 things that I'm aware of which are not included in multi-category. Now, I don't know how many of you are familiar with relative monads, and I definitely don't have time to go into that in this talk, so I'm really just kind of sketching this, right? So Alton, Kirchhoff, and Oosterloo defined the notion of relative monad on a functor. So instead of having a monad on a category, you have this relative monad, they call it, on a functor. And I'm calling it forwards relative monad, because there's another paper by Spivey which does something similar, but goes the other way, backwards relative monad. In fact, these two things can be subsumed into a single concept, which is relative monad on a bimodule. That subsumes the forward and the backward. I should say that the forwards relative monad was studied in a lot of detail by Archer and McDermott in the past few years. They have at least one long paper investigating this. So this one actually generalizes the previous two, so we can largely ignore the first two. Well, I don't know, because there's interesting things to say about them, but this one does subsume forwards and backwards. Then there's sequencing model of code by push value. Again, I'm not going to define this, but what I just basically mean is you take the syntax that I showed you before and you just crudely write that down into a categorical structure. You've got a class of value objects and a class of computation objects interpreting the value types and computation types. You've got a category representing the context. You've got some structure between them, and then you just literally have some sets for the values and some sets for the computations, and you just follow the rules naively. And then lastly, you've got a category on a class span. So again, that's another one that I'm not going to define. It's just a variation on the notion of category. And this one is actually a bit artificial. We introduced it for this paper just to have something relatively simple to see what's going on, because the call by push value sequencing is a bit complicated and this one is simpler. So it's just an artificial example. But this, of course, is the one that I've used to motivate this talk, the sequencing and call by push value. Okay, so I've given you 5 examples, or you could say 3 examples, of things which are excluded by the multi-category framework for what a monoid is. But we want them to be monoids, nevertheless. So the story is that we started at the multi-category framework, monoid in a multi-category. We're going to generalize this in 2 steps. First of all, we generalize it to left skew multi-category, and that will include all the relative monads. The most general kind, which is relative monad and bimodule, will be seen as monoids in this level of generality. But that's not good enough for the call by push value sequencing. So we have to go another level of generality to bi-skew multi-category, and this gives us the last 2 examples. That is the story. Okay, so left skew multi-category was introduced by Burke and Lack in a paper that was very enlightening to me, because before I saw this, I was really confused by this skew stuff. But anyway, this made it all clear. So in a left skew multi-category, it's like a multi-category. But, so you have class of objects. Morphisms go from a list of objects to an object, but there's 2 kinds of morphisms. You've got the loose morphisms, which are just written like basically normal morphisms in a multi-category, again, from an object list to an object. And then you've got the tight morphisms. A tight morphism goes from a non-empty object list, and I'm sure you're completely unable to see that we have a double arrowhead there, which as a convention in this paper indicates a non-empty list. Okay? It's, yeah, right, sorry about that. I can't think of anything better, but anyhow. So what we try to do is that we want to highlight, if you like, that we put a bracket around the left half of the leftmost input. It's the leftmost, it's not really the leftmost input which is special, but kind of the left part of it, if that makes sense. It's just like a pictorial intuition. And just to emphasize it, we also put a red blob on the side of the triangle. Right, hopefully that's enough emphasis. So we've got this bracket covering half of the left input and also a red blob. Right. We have a loosening operation from, so any tight morphism can be turned into a loose morphism, and we use acute for that, acute symbol for that. Now, this is generalizing multi-category. So if we were to have an ordinary multi-category, then these 2 Hom sets, the loose Hom set and the tight Hom set, would be the same. I mean, in the case that this list is non-empty, right? And then the loosening would just be the identity. So the loosening of F would just be the same as F. On each object, we have a tight identity. Remember, we can loosen that, so we also have a loose identity. And we have 3 kinds of composition. It's like, just thinking pictorially, these are the only possibilities. You can put a loose, this is loose composition, where you're putting a loose thing into a loose morphism. Or if you've got a tight morphism, you can either put a tight morphism on the left or a loose morphism in the middle. So you see, everything has to line up. You don't want to have a clash between having you couldn't have a red bullet here because there's no red bullet underneath. So it wouldn't work. And then you basically write down all the possible versions of associativity and interchange and identity. And it's just, you just write down all of them and you require those. This is all in the paper, right? So you just say all the possible laws. In particular, you want to say that everything commutes with composition, like this commutes with loosening, and this commutes with loosening, right? So we've defined left skew multi-category. Again, this was taken from Burke and Lack. They didn't actually write it out this way, but that is, in effect, what it is. Now, if you're not familiar with, I said before that you could ignore my slide on monoidal if you didn't know about monoidal categories. I suppose you could ignore this slide if you don't know about skew monoidal categories. So, but maybe you do. So left skew monoidal category, this is an older notion than left skew multi-category. Here, you don't, it's like monoidal, but you have 3 coherence maps which are not required to be invertible. And you've got some, I think, 4 coherence conditions. And they showed that if you have a left skew multi-category with left tensors, again, that has to be defined, I'm not going into it, that corresponds to a left skew monoidal category. So a version of Hermida's result. The main reason I mention this actually is that if I didn't show you this slide, you really might wonder from this definition why on earth it's called skew. It seems like a very strange name, right? But it's because of this connection that it's called skew. Okay, that's all I want to say about skew monoidal. Right, going back to left skew multi-category. So now you can go through and define monoid and just make everything tight wherever you can. So if you think of the multiplication, you make it you require it to be tight. But the unit is nullary. Obviously, a nullary thing has to be loose. You can't have a nullary tight map. That doesn't make sense. And then I'm not going to write down all the laws, but look at the associativity. You keep everything tight where you can. Here, on this side, you have to loosen M in order to be able to do the composition. So you just write down the obvious things, keeping everything tight as much as possible, because you can always loosen afterwards, so it's not a problem. You're not losing anything. Okay, that's left skew multi-category. So the basic idea is that you have special morphisms where the left-hand side of the leftmost input is highlighted as special. 5 minutes left, okay. You also have okay, now we finished that level. That, as I said, includes relative monads, all the different kinds of relative monads, which I've not told you what they are, sorry about that, but anyway. Bi-skew multi-category, this is the next level. This is the new thing in this work. So we have 4 kinds of morphism. Morphism can be, tight on the left or loose on the left, and it can be tight on the right or loose on the right. So all 4 things are possible if you see that in this case, A could even be empty in the loose case, but in the other 3 cases, A must be non-empty. You can see that double arrowhead, which is so visible, right? And again, you think of this bracket as being on the left half and this bracket as being on the right half. So it might be that this is length 1. So you're highlighting the left half and the right half of the same unique input. That's an important case. For the identity, for example, is tight. You have left loosening with acute and right loosening with grave, and they're required to commute. If you start off with something like this, you could go there and there, or there to there, and you get the same. And again, you work all the different kinds of composition. You can write them all out. I can't remember how many there are. It's all in the paper. And all of the millions of associativity and interchange. You just have to work out all the possibilities and impose all of those conditions. That's bi-skew multi-category. Okay, and now we want to define monoid and homomorphism in a bi-skew multi-category. So what do? We make everything tight if possible. So the multiplication is tight, right? The unit is nullary, therefore it's loose. The associativity, again, you see you've got some left loosening here and some right loosening here, but you keep everything tight as far as possible. And now try and go back, remember what I said about the associativity in core by push value. Remember I said the left is special in one way. That's this red dot or left bracket thing, right? The right is special in a different way. That's this right bracket or red dot. Maybe we should use a different color for the right, I don't know. Maybe that would have been sensible. Okay, so the left is special, the right is special, and you see it. So I'm not, okay, so now the extra bits of abstraction. Am I running in, just to say briefly, we've got a coherence theorem. No. Okay, we've got a coherence theorem. It's like this. You define an unbiased monoid to be in a bi-skew multi-category C. An unbiased monoid is simply a map from 1 to C. What does that mean? It means instead of just having nullary and binary multiplication, you've got multiplication of all arities and all possibilities of tight and loose, and everything, all the compositions of multiplications give you multiplications. And you then show that every monoid uniquely extends to an unbiased monoid. This fact for multi-categories is well known, so we're showing the same thing works for biskewed multi-categories, and so that's, if you like, it's reassuring. It tells you we're not missing anything in our definition of monoid. That's one thing I wanted to tell you. Also, I said that they define, Burke and Latt define left skew multi-category, and we've got this new concept of biskew. Well, it's not quite, that's not, you could see it a little bit differently. They actually had a higher level of abstraction of T multi-category, where T is a certain kind of operad, and then they define left skew multi-category to be an R multi-category for a specific R. Right skew multi-category is exactly the same, you just turn R, you'd have the same operad, but you reverse left and right. And so all we're doing is multiplying these two operads. So actually, all the ingredients that we use to build biskewed multi-category are already there. This was really amazing to me. You start with call-by-push value sequencing, and you end up with this just multiplication of operads that just gives you, then apply it to their notion of multi-category, and you get biskewed multi-category. So it was all kind of there. They don't talk about monoids, but biskewed multi-categories are kind of implicit in what they did. Okay, so those are some little extra abstract treats. Let's conclude. So now, every monoid-like notion that we've come up with, I'm aware of, that Morgan and I are aware of, is actually a monoid. So now we have a new saying that call-by-push value sequencing is just a monoid in the particular biskewed multi-category that we define in great detail in section 5.4. What's the problem?
Can you compute something like free monoids in a multi-category, biskew multi-category?
Well, the free monoid honestly, I have no idea. I hadn't thought about that question. I mean, they don't always exist even in a multi-category, right? I mean, you can define a notion, which sometimes will exist. I don't know, I'd have to think about that. Sorry, I'm like... Yeah, good question. Thank you.
Is there an intuitive reason why both these forwards and backwards relative monads were both part of this left skew multi-category instead of needing sort of these left and right skew things?
Okay. No, I mean, I wouldn't say they were left and right. I called them forward and backwards. So you got a functor from C to D in the one case and a functor from D to C in the other, and each of those gives you a bimodule from C to D. But they've very much got one direction in terms that you take objects in C to objects in D in both cases. So they're really going the same way.
So you only need the biskew thing where you have both things going on at the same time.
Yeah. So the point. So what was distinctive in the call-by-push value sequencing is that there's something special on the left and something special on the right. You don't get that with relative monads. It's only really special on the left, but on the right, there's nothing special going on.
Okay, thank you.
What is a group?
Oh, gosh. I thought, okay, come on, you could at least have said what is a commutative monoid. Even that would have been too hard. I don't know what a group is, sorry. None of these things seem to have commutative variants, actually. So at least these one right here, so group, no, sorry.
So, nice talk, thank you very much. Have you learned anything about call-by-push value from these investigations?
Actually, I learned a lot, but not in not really from the by SKU stuff. I mean, learning about the multi-categories, particularly about exponentiability in multi-categories, which does apply to some extent in the SKU case, but this was new to me, and it led me to understand the connection between like locally indexed models of call by push value and graded models in ways that I didn't before. So I learned a lot, but it was completely sort of by the way, and it's not stuff which is sort of in the talk. See what I mean? So that's probably not very helpful. But the process of like learning and writing about this multi-categorical story actually was very educational, yes.
So yeah, I just want to mention something that here the multiplication you described would be defined as composition. Would be described usually as composition of morphisms. Yes. So like you have different programs or maps, and you compose them. So multiplication is composition of programs. Yes, you would agree with that?
Well, I mean, you could call it composition, but
I mean, traditionally.
Yeah.
Yes. So what I mean is that, in fact, the question you ask is, what are the different kinds of categories?
Yeah.
Yes. What are the different kinds of categories that we could use? So we could imagine skew notions of categories, where we have special left maps and right maps. And I think this is the kind of universal question we are exploring, how to go beyond. And people have done that in infinity categories. So they work with simplices, simplicial sets, and as generalizations of categories. So do you have any view on that? Like, for instance, here today we spoke about like diploids and non-associative categories. So, some general notion of category, more general, non-associative maybe, or whatever, with left maps, right maps, that would organize this.
Okay, I didn't think of this as a generalization of category, because I thought it was a generalization of multi-category, where we still have all the, as I said, when we define bi-SKU multi-category, we have all the associativity and interchange and identity laws. And what's changing is that we have more kinds of HOM set. But maybe there is a connection there to what you're saying. I think that could be.
I think it's time to thank the speaker.
Yeah.
That was very interesting.
to this synthesis to session. We have 2 papers ahead. So the first one is from Xiangyu Peng from University of California, San Diego. He's going to present Nice to Meet You, synthesizing practical ML-IR abstract transformers. Please.
Hi everyone, I'm Xuanyu. Today I'm excited to talk about our work, Nice to Meet You, synthesizing practical ML-IR abstract transformers. And this work wouldn't have been possible without my amazing collaborator from the University of Utah and UC San Diego. Okay, at a very high level, all of this talk is about automated abstract interpretation. Because enormous effort have been put into the development of static analyzers based on abstract interpretation. And to be more specific, our focus is on lightweight, fast abstract domain that can be actually used in the data flow analysis in compilers. And our design goal is bulk automation, which means we want to minimize the user input. And our dream is to automatically generate an abstract interpreter just from the language and the abstract domain. Okay, I guess most of you have been very familiar with abstract interpretation and abstract transformers, but just let me briefly go through this basic concept. So in abstract interpretation, we need an abstraction function to abstract a set of concrete value to an abstract value. And we also need a concretization function, which maps an abstract value back to a set of concrete value. So to analyze a program in an abstract way, we need to implement the abstract version for each operator, like inc here in the program. This is what we call abstract transformers. So for example, inc add 1 to an input, and its abstract transformer could be add 1 to left and right endpoint respectively. And technically, you can also only add 1 to right endpoint, and you can even return the entire integer domain, but it makes the abstraction less precise. So the thing we want to automate it is to automatically synthesize a precise abstract transformer from the concrete operator. So let us see why this problem matters in practice. So these are 2 abstract domains widely used in LLVM. So first, known bits, they are just partial bit vector. So every bit can either be 0 or 1 or just unknown. And constant range, they are just integer interval. Sometimes they have 2 versions for unsigned and signed arithmetic. But the challenging thing here is that, so to enable the analysis, so given abstract domain, every operator in your language needs such an abstract transformer. That's not good, because in LLVM IR, there are already 40, we'll say, basic operator, and even then, the coverage of those abstract transformers is not 100%. And moreover, these transformers are very hard to write. You can see that those source file contains thousands of lines of code. And beyond that, there are even thousands of LLVM intrinsic, which you can understand as some platform specific instruction, which could be equipped with a transformer, where the current coverage is very low, I guess less than 1%. So this gives a large room for synthesis. But another thing is that writing those transformers is tedious and error-prone. So even for simple operator, so let us get a sense of how complicated those transformers could be. So addition, very simple instruction. Then what does its norm-based transformer looks like in LLVM? Well, this is just part of code. It has hundreds of lines of code. And initially, I want to understand what's going on here. I translated it to expression. Well, still unreadable. And I guess if you were Patrick Kusel, you may understand what is going on here, or even you may be able to derive it by yourself. But I certainly cannot. But this is where Nice to Meet You come in. when given the blue box on the left, automatically synthesize a yellow box on the right. So nice to meet you, give you a precise transformer. So at this point, I would like to show you a preview of our result. So although our main goal is to generate transformers for those operators that that don't have one yet, we also wanted to see the quality of the synthesized transformer. So we compared them against those human-written existing transformer that in LVM. And the result turned out that in some cases, our synthesis transformer are actually more precise than LVM ones. And in some other cases, the synthesized transformer by itself is less precise, but it still adds precision when combined or meet with the LVM's transformers. Now let me talk about this problem a little bit more formally. So this synthesis problem can be stated as we are given an abstract domain and the semantic of a concrete operator. The goal is to synthesize the most precise abstract transformer for that operator. And notice that usually for one abstract domain, there are like a lot of concrete operators that need abstract transformer. So however, to compute the most precise result is expensive. You already know the transformer that naively doing that is the so-called the best transformer. And intuitively, it works by first concretizing the abstract input and applying the concrete operator over those input and then abstracting it back. But as you can see, this process requires enumerating all possible concretization of an abstract value, which make it impractical to be used during analysis. So we need to find a efficient representation for this, but sometimes this is very difficult and even unachievable. So we tend to find the over-approximation of the best transformer. In terms of interval, you want your transformer output at an interval that covers the best interval, and also be as close to the best interval as possible. Just like the blue circle here approaching the black one. And notice that this over-approximation should hold pointwise for input 1, input 2, input 3, and so on. So how does nice to meet you actually find such an over-approximation and make it as tight as possible? So our method mainly relies on 3 insights. First, we treat the synthesis problem as an optimization problem. We define a quantitative objective to characterize how sound it is, how precise it is, and we optimize them jointly. And the second insight, which is the key, make nice to meet you scalable, also where the name nice to meet you comes from, is that we leverage the meet operator in the domain. So we synthesize one transformer at a time and take the meet instead of synthesize a large one at once. And the third insight, conditional abduction, refers to the case that if we happen to find some highly precise transformer but only work for part of the input and it is unsound on other input, we tend to find a predicate to divide the input space to make it globally sound. So let's step into this insight one by one. So first, we introduced a quantitative objective that measures the imprecision of a transformer. Specifically, it is defined based on the imprecision of its output abstract value across all input, which can be understood as the total area of those blue region. And for example, in interval domain, you can just use something like interval length. And the goal then is to synthesize a sound transformer that minimizes this imprecision. And to generate a transformer candidate, we use a technique called staccato synthesis that have been applied to super optimization. So this basic idea is we start from a program that filled with random content, and at each step we mutate it and hope we can find a better one. Yeah, very simple. So here, each transformer is represented as a SSA form program with a lot of available instruction you can use in your DSL. And in each mutation, we randomly mutate one operation or one operand in some operation. Okay, so this stochastic synthesis algorithm essentially follows the MCMC process. The idea is to maintain a current transformer, and at each step we mutate it. And then we compare the cost of their cost. If the new one has a lower cost, we're gonna accept it. And if the new one has a higher cost, we may still accept it with some, but with some probability related to how worse it is. And the cost function here combines both soundness and the precision using the metric we defined before. And this MCMC process help the synthesizer to avoid get stuck in local minima because it sometimes accept a program with a higher cost. Great. So build on top of this, the key insight is to synthesize the meat of a set of transformers. So intuitively, the meat operator can combine information of two or more analysis results, and yield a more precise one. So for example, in known bits, if you know the first bit, if you know the second bit, then you know the first two bits. And for the interval domain, it's just the set intersection. So generally, the meat operator is like the set intersection here. When you intersect two blue regions that both cover the black one, the result is guaranteed to be smaller and still cover the black one. And actually, this is also how LLVM developers write transformers. For instance, here is a transformer for the on-site reminder operator. You don't need to read this code. Just to know that it is made up of several smaller pieces, each capturing a different heuristic that can improve the precision in some cases. So probably we can synthesize. And the way we do that is to incrementally add new transformers that have non-zero precision over existing set of transformers. The precision part of the cost function is actually the improvement brought by the newly added transformer. And for example, if you already synthesize F1 and F2, and now you get an F3, the red region represents the precision improvement. And another innovation of our approach is using abduction to refine unsound but precise transformer. So let us zoom in this LVM transformer again. And so some of its mid components include the conditions where the body is an unsound transformer that only works for certain inputs. So for example, like the one shown here, it is sound over the left 3 input, but unsound on the right 2. So therefore, in Nice to Meet You, we also have a stage to stochastically search condition, like the C here, to make this, to construct a new transformer that is globally sound over all input space. So here is the overall workflow. The user supplied the abstract domain and concrete operator. And Nice to Meet You start working on that and until find the best transformer or reach some time budget, then provide the transformer for you. And the candidate program I expressed in MLIR dialect called XDSLSMT. So it is in SSA form, and it can be lowered to C++ for execution, for fast execution, and to SMT formula for verification. And the synthesis engine runs hundreds of MCMC processes in parallel, and each process continuously mutate and evaluate the transformer. And after that, we will get some candidate, and we then send them to the verifier to guarantee their soundness up to a high bit width, as the cost function is was only estimated on some sampled test input. And this ends up with two groups of candidates, sound one and unsound but highly precise, unsound but precise ones. And we repeat this process until time budget. And finally, we output the meat of all of our transformers. So now you may wonder, does this really work in practice? So to answer this question, I'm going to show 3 parts of our evaluation. So first, we have this precision comparison over basic operator in ALV and IR, which I have shown at the beginning of this talk. So one thing I want to add is that so more than half of those operators in LVM, they are already reached the theoretical best, which means there's simply no room for us to improve. But even for the remaining operator, nice to meet you can fill some edge cases in those LVM transformer, which has been maintained and highly optimized for decades. And beyond that, we also want to see some practical results. We do this end-to-end precision evaluation where we plug our synthesized transformer into some data flow analysis framework to analyze some real project. So on the left, it is the analysis result using the MIT of synthesized transformer and the LVM one. And we can see that a synthesized transformer helps us to discover a little bit more known bits. And on the right, we compare synthesis transformer against LVM separately. Result shows that, well, the synthesized one got lower precision, but it got very close to the LVM human written one. But what I want to stress here is that the goal is to not beat LVM. So just to be competitive, because now we have a push button tool, and using our tool for a couple of hours will give you a nice-ish abstract interpreter where a human developer may spend days or weeks to implement the same thing, or just choose not to do that due to the time limits. And here is an example of the case where developers usually don't have time to do. So we all know that simply compose the transformer of 2 operators is less precise than one transformer that abstract the composite function. For example, this is how people use those basic operators to implement absolute function. But if you use the transformer for of this basic operator like logical shifting left, addition, XOR, you will get a very low precision because you lose precision every step of composition. It is just that the human developer don't have time to handle this, to write transformer for such kind of composite patterns. But we have nice to meet you. We synthesize a specialized transformer for them. And also for some other patterns, we mined from some code corpus. And the result turned out that it is very easy to get a large improvement. It's not surprising. So at the end, I want to highlight that synthesis really changed the engineering economics. So to wrap up, I talk about the transformer synthesis problem. I talk about our approach and our evaluation. But this is just the first step to our final dream, which is to automatically build an abstract interpreter for users. And so for the future work, we want to consider the efficiency and the readability and the maintainability of our transformers. And we also want to get LLM, the most powerful tool, into our better transformers. For example, the popular alpha evolves things, something like that, to replace the submodule that produced the transformer candidate. But the meat inside still works here. And we also want to have our cost model not only consider the precision of a test input, but consider the actual analysis result of some real project. So to put our work into context, here is some related work. So the first one, the POPL'22 paper by Kalita et al., is the first one who proposed the problem of synthesizing abstract transformer, which largely inspired our work. And the rest are some works that synthesize transformers for different domains. But our tool provides bulk automation for generating transformer with a minimal user input and to make it agnostic to specific domain. So yeah, that's all my talk. I'm happy to take any question.
Thank you for the talk. Any questions? Sebastian.
Thank you. I don't really understood well what you have to give to the tool. So when you say you have to give an abstract domain, does it mean you have to give abstraction and concretization function, meet, join?
Yes, you need to provide those things, like those components that consist of abstract domain. Yeah, okay. Like what do you say?
And the input domains where you basically it's synthesis by example. Mm-hmm. Which example do you choose? Is it the Monte Carlo which will create the example, or do you give some prior examples?
Well, so this framework is not tied to specific domain. And in detail, you need to provide things like abstraction, concretization, meet, and also how you represent your abstract domain in a framework. Like, yeah.
Thank you for the great talk. Mm-hmm. In your experience, how many abstract interpreters, abstract transformers did you need to meet together in order to like get the performant and precise abstract transformer?
So we don't limit I would say the number of the meet components. So the algorithm is basically keep generating a lot of candidates, and if some of them have non-zero improvement, you add it to the set. But then at some point you will find that, okay, so some of them are useless, right? You can remove it. And so in terms of result, it's usually end up with from 1 to 10, a reasonable size. But this also brings some efficiency issue, but you can easily choose, say, like top K transformer, like K, where K you can choose by yourself between a trade-off between efficiency and precision.
Okay, I have a question. So which abstract domain you have evaluated for, or like outside interval, like did you evaluate for like zones, octagons, or more explicit domain like polyhedra? Or like for those, I think generating the candidates for abstract transformers might be easy, but how will you verify like the soundness and even compute like the precision of those in those domains?
If I understand correctly, you're asking for those relational abstract domain. And is your question why do we support those relational abstract domains?
If you do support, how you like verify like the soundness and compute like the cost of precision then?
We do consider this problem. I think it theoretically supported that. We choose not to do relational abstract domain just because.
So what I understand, like computing like volume for relational abstract domain is extremely hard task, right? I don't know how, like for polyhedra, you cannot compute like the volume very easily for like even for smaller dimensional things.
You mean like compute the imprecision?
Yeah.
Yeah, that's one reason, and actually there's some other practical reason. It is very hard to actually synthesize transformer for that. But yeah, it is an interesting future. Yeah.
Thank you.
Okay, last question.
Thanks. I was wondering, so my understanding was the algorithm starts by sort of producing random programs and slowly optimizing them. Have you tried taking the examples where you have an existing implementation and using that as like a seed? So I'm particularly thinking the composite operator scenario. You always have, if you have already have like best transformers for the components, you already have like a starting candidate solution. Does that help your tool, or is it actually just send it down the wrong route?
That's a really good question. Yeah, we try to use some existing transformer as seed. Yeah, it can like improve the precision a little bit, but I think the better way to do that is you put the existing transformer in your set, in your mid set, and then you focus on how to improve this transformer by adding more components to that. And in terms of this approach, we can always make some small improvement for those, if your existing transformer is not 100% precise. Yeah.
Thank you. Okay, let's thank the speaker again.
Thanks so much.
Actually connect.
This. Okay, my mic seems to be working.
Mine not okay. The next speaker is Benedict, and he's going to from Graz University of Technology. He's going to present parameterized infinite state reactive synthesis.
Yeah, thanks for the introduction. So let me first talk a little bit about what this title actually means. So yes, most of you are more interested in like sequential programs or functional programs where you take inputs once and then do some complicated computation, and they're interested in one output afterwards. Oh, sorry, let me double check. It was working before, sorry for that. Okay, sorry for that. Let me start again. So we're interested in reactive systems. So what do I mean by reactive system? So as I said before, we're not interested in a single function that takes inputs at the beginning and computes some result in the end, but instead we're interested in a system, like you see here, that is interacting with some environment. So in every time step, it receives some information, some inputs from an environment, does some computation, can update some of its internal state, and then it sends back some result of this computation to the environment. And these two parts, or sometimes also referred to as players, are interacting continuously with each other. And this gives us some infinite trace, so if you don't stop it, then it just keeps running forever. And you're interested in specifying the behavior of this system over these infinite traces. And then we want to synthesize some system or some program that satisfies some specification over this computation trace. And we will use something called temporal logic, or a form of temporal logic, to specify these expected behaviors. And then we want to find one program that actually satisfies this for all possible environments we could use. So let me show you a small example. So we have this cute robot here that is standing on some track. So let's start by modeling this in form of temporal logic, or in the infinite state temporal logic. So let's first introduce a state variable, let's call x, which is a real valued variable, and it defines the position of the robot on the track. And then the robot should also be able to do something. Just standing there is boring. So it can move to the left or to the right, or it can just not move. So this gives us 3 possible actions that the robot can choose from. And now I also said there is some interaction with an environment. So let's add some adversarial environment to that. So we have this little daemon here that is trying to push the robot around. So it can also push it either in one direction or in the other direction, and it can choose any value between -1 and +1 for pushing it. So this might also be some fractional value or something, which results then in an infinite state system. So now we have the options for how the system can behave and how the environment can behave. So now we also want to as I said, specify what is a good behavior of this system. So the first one is we don't want our robot to fall off the track. So the daemon should not be able to push it off the track. So let's add an invariant that in every time step we have to be on the track. But just staying there is not very productive. So we want our robot to also do some work. And for that, or in this example, it should move boxes from some pickup area and load them onto a ship. And in an abstract sense, we'll model this by just being in the area where the boxes are and being in the area where the ship is, both infinitely often. And this infinitely often in linear temporal logic, which we're using here, is notated by this square and diamond operators. So here it says be in both regions infinitely often. And if you look carefully and think through this example, you might notice that this isn't really implementable as it's shown here. Because what if the robot is just constantly pushing with maximum force in one direction? Then we cannot move and get anywhere closer to the target. So we'll also extend our temporal logic specification by adding some assumptions on how the environment should behave. In this case, it is we expect the environment to both push in the left direction and in the right direction, again, infinitely often. And this specification that results there falls then into a fragment that is called tier 1, which has these like some things happen infinitely often as assumptions and also on the guarantee side. We'll need a bit of this structure, but the exact details aren't super important for this talk. So one thing that this tier 1 structure gives us is we can take this formula that we had before for the temporal logic formula and get some first sketch for how an implementation should look like. And the first thing is we introduce a new variable. Here it's called C that keeps track of if we are trying to pick up a box or if we are trying to load the box onto the ship. And then we get two strategies, one for go into the area of the box, and the second one for go into the area of the ship. And also we have a third component, which is shown at the top, which checks if have we currently satisfied one of our guarantees, then we should change our strategy and work towards the next goal or the next strategy. And in this case, these just alternate, and if both of them reach their goal whenever it's their turn, and they change between each other, then we would have a strategy that infinitely often reaches both of these targets. So now let's try to fill in these if conditions, and just if you do it manually, we could, for example, plug in this. If you just focus on the highlighted area, then we would have for reaching the boxes, we should go to the left as long as this would not lead us to falling off the track. In that case, we just stop, and if you want to go left, then there is never a reason to go right. And the other strategy for getting to the ship works, works the same. Like, you can also remove like the false branches, and I'm using this program from now on. So the other part of the title was parameterized. So what do I mean by that, and why do we need that? So previously we had this example which was like with between at 1 is one area, at 9 is the other area. But what if I change this? What if my pickup area got moved to the location -2 and the boat got moved to the position 6? Or what if the ship or the boat is now 1,000 units away? I don't really want to rerun my synthesis tool with these new parameters, or whenever I have a new environment, rerun the synthesis tool. So what I want to have instead is one parameterized program for this one parameterized specification. So here I can now say I have parameters like min and max that define some properties of my environment or of the problem in general, like the position of the boxes or the position of the ship. And then I want to have a single program that might use min@max and that works for all of these possible values I can plug in for min@max. So how do we tackle this problem? And for that, we have two key observations. The first one is that if you use a tiny state space for this problem, then it's not too hard to synthesize this. So like high complexity, but a small state space means it's still tractable. And the other observation is that the programs aren't that different. Just because I change a few numbers in my specification, I expect very similar output programs. So we want to exploit these two ideas in our algorithm. So our algorithm starts by plugging in some concrete numbers into this parameterized specification. And then we can run this through an existing synthesis tool, like a GR1 synthesis tool that works on these infinite state systems. And this gives us one concrete program, and it also gives us a certificate or an invariant that certifies that this is a correct program for these concrete values. Like, for example, using 0 and 2 gives me this program. So I have now, for the left program, the condition x plus d should be greater or equal to 1. Then I should go left. But now I need a second program, because just from this one program, it's a bit difficult to do anything. So let's repeat the same process, plug in some different numbers, and again, we get a concrete program and invariant or a certificate why this is a correct program. So now I change the numbers, and the program is almost the same, but there is some slight differences in there. So now that we have at least two programs and two certificates, we can try to generalize them. So from these example programs for concrete states, we want to infer one parameterized program that should work for all possible parameters. And also a certificate that is trying to certify that this program is actually correct. So let's first look at how we generalize these strategies. So how do we get from multiple concrete strategies into one candidate for a parameterized strategy? So we saw that these templates or this sketch we had for the program had like if conditions, and otherwise it was choosing between the actions. So we can now start by generalizing each one of these conditions or guards individually. So let's look at the two examples that we had before. So for 0 and 2, we had the condition x plus t should be greater or equal to 1. And for 1 and 3, we had x plus t is greater or equal to 2. So the first step in this generalization algorithm is to apply anti-unification to figure out where these guard conditions are the same and in which parts of the guard conditions they are different. So this would give us a new expression as shown below that says x plus t greater or equal. This is this shared between all the guards that we have seen. And then there is a whole that sometimes is 1 and sometimes is 2. So now we did a second part of our generalization approach that figures out what should we put into this hole. For this, we rely on syntax-guided synthesis, and we ask it just to, given that we know the values for our parameters and the values for this hole, can you come up with an expression that neatly expresses this difference? So here it might come up with maximum -1. It's a small, nice-looking expression that satisfies all the criteria that we have here. So to summarize this generalization part, we first have an anti-unification preprocessing step that figures out which parts of an expression are already the same. Then using syntax-guided synthesis, we synthesize new expressions to fill the holes left over by the anti-unification part. And we also have a fallback method if we figure out that something is too different to work with this approach, then we more or less generate a decision tree, which I did not show in detail here. So using this method, we can apply it to the whole program, and we get this first candidate for the strategy. So here we have both programs more or less use the same condition. So both say x plus d, or like the inverted, but both use max minus 1. This kind of looks a bit weird, right? So if we want to go towards the boxes, our program just depends on how far away we are from the boat. And if you are close to the boat, that's not quite what we want. And that's where the last part of the algorithm comes in. We need to take the program and the certificate and cross-check those and see if we are actually found a program that generalizes to all situations that we might encounter, like to all parameter values. And doing so, we would figure out, no, that doesn't quite work. I'll go into a bit more details on how these certificates look and how we find these counterexamples in a moment. But for now, just accept that no, this is not, this left sub-strategy doesn't really work. And we get new parameters like -4 and 0 for which it does not work. And now we can go back to the reactive synthesis module, the tier 1 synthesis module, and ask for a new program for these parameters. So we now get a third program, and we can now also include this in our generalization approach and infer this program that now fixed also the left sub-strategy and uses a more appropriate condition there. So as promised, how do these certificates and this cross-checking work exactly? So the first part is we have invariants. These we get automatically from the tier 1 solver. So we can just take these invariant expressions and also apply the same generalization as for the conditionals in the program and try to infer a new invariant that works for all the parameters we have already seen. And then we also need to somehow certify or check that we are actually reaching the guarantees. And this we do with a ranking argument for each one of these sub-strategies. So each of these sub-strategies should make progress towards the goal it is supposed to reach. And then after we have the ranking function and the invariance, we can ask an SMT solver, does this actually work for all possible parameters? So for these ranking functions or termination, we have like this loop. So run this sub-strategy until you reach the goal it's supposed to reach. And these ranking functions are like mostly standard ranking functions, so they should decrease in every step. But because we also have this tier 1 part with the assumptions, we need to like add a bit of plumbing to our ranking function that says for at least one of these assumptions we have on the environment, we should make progress. And otherwise, if none of the assumptions are true, we can also just stall. So based on the first program, we could get this ranking function candidate, where our ranking argument would just be x. We are always making progress by decreasing x, but that's not quite right, because as we would expect the ranking function should be positive, or like greater or equal to 0 or something. And x could be negative, like if we have -4 to 0 as our range for the problem. So we would get, when cross-checking, we would get these counterexamples. And then after we integrate this counterexample in our generalization approach, our ranking function synthesis should also come up with a better ranking function. And these, like this x minus min, would then also be a ranking function that correctly certifies this sub-strategy. So to summarize the procedure quickly, we start with the parameterized specification. We generate multiple concrete instantiations of it, and then run them through an existing synthesis tool, and then try to generalize both the programs and the proofs, and then cross-check them if we have found the correct program and proof pair. And if not, then we get some new counterexamples. Unfortunately, this whole process is also undecidable, so it might happen that we just run through this loop forever and just generate an infinite amount of new examples. We also implemented this in a prototype tool, and so it uses CVC5 for the Cygos part and C3 for the other game solving. And we have made also a different variant that skips this anti-unification part and just tries to do the whole generalization only with Cygos. And we also compared to existing tools that don't support like this parameterized framework, but where we try to encode this with existing elements. And we have a small set of somewhat existing benchmarks that we added, where we added some parameters into it, some new ones that we created for this paper. And like the overall observation is that existing tools that don't natively support these parameterized specifications, they almost fail completely. So if one solved one benchmark, the other solved two benchmarks. And our tool solves most of these benchmarks in the configuration where it uses anti-unification preprocessing. If we turn this feature off, so just rely on Cygos, then about half of the benchmarks fail. Like all of them, the benchmarks that have a bit larger expressions, just using Cygos alone is not sufficient to find a good generalization. Okay, so thanks for your attention, and I'm happy to take any questions.
We have time for a couple of questions. Please.
Hi, great talk. I'm curious, so anti-unification relies on like all of the program structure matching other than that parameter that you're anti-unifying.
Yes.
Right? And so, but the synthesizer can kind of spit out programs with all kinds of different structures. So I'm curious if you run into that issue a lot, if you have to do things either modifying the synthesizer to handle that better, or like canonicalizing, or yeah.
Yes, so there is quite a bit of normalization in there that I skipped over here. So one advantage of this, like just restricting ourselves to the tier 1 synthesis part, is that we can really use this this template here. Where is it? Like this one. So the important, we already know that like we have one condition for each action and each sub-strategy. So this reduces the variability of the synthesis output already quite a bit. And then we also do some redundancy elimination on the SMD formulas that we get, so removing all kind of propositions that are not necessary, and they still preserve equality. And then we are also like sorting all commutative operators like alphabetically, so all the same variables should end up in the same position of the formula. But this is a bit of a heuristic, yes.
Nice speech, and in my understanding, there is a two-part generalization and verification. Yeah, and I found out that you synthesize a ranking function in the verification process, and I wonder why it is separated. I mean, the ranking functions cannot guide the generalization process.
why do we have to find these ranking functions in this verification part? Why are we just taking them from the synthesis result? We first tried just taking like the iterates from the fixed point computation, but it turns out that those have like too much strange behavior in there, in that they are not just specifying a single program, but like all multiple possible implementations that would still be compatible with the results of the fixed point computation. And these kind of turn out to be too complicated for good ranking functions. And we want something that doesn't rely on how many iterations we did in our first synthesis. So like the synthesis approach tells us, okay, this is the set of ranking functions for rank 0, these are for rank 1, and these are for rank 2. But just having those 3 sets doesn't generalize on its own. So you need something that from knowing the first 3 sets of the ranking argument, figure out what is the 4th and 5th and 100th one. And for that, we're currently relying on again on Cygos to figure out some ranking argument.
You probably mentioned this, but I just didn't catch it. What is the specific structure in this like reactive type of program that you're using? Because the big synthesis loop that you're showing, I can imagine, could be applied to any sort of parameterized program that is just like mapping some inputs to outputs.
Yes, you like. Where's my full overview slide? So this whole procedure with having a parameterized program and then just plug in some different synthesizer here. I think, yes, this would work in principle. It's mostly that we started from this reactive synthesis perspective. So we also spent some prior work on developing this first synthesis tool. And I think you could try doing this with other tools. So if you want to talk about that, I'm happy to do this afterwards.
Okay, we are running out of time. If you can speak later, maybe. Okay, sorry. Let's thank the speaker again. Okay, this session is already over, and for those interested, there is the report and business meeting in the main room.